All right, get ready for a wild ride because today we're diving deep, and I mean deep, into a mind-blowing corner of quantum physics where, well, let's just say things get a little weird. We're talking about the possibility of time running backwards, like actually backwards.
Yeah, it's not exactly Back to the Future, but this experiment definitely has physicists scratching their heads about how time really works, at the most fundamental level.
Okay, you've definitely got my attention.
Yeah.
What's got everyone so fired up in the world of physics?
So, researchers at the University of Toronto, they've done something pretty amazing. They've managed to observe, or at least it seems like they have, a photon, which is just a tiny particle of light, spending a negative amount of time, get this, interacting with a cloud of atoms.
Wait, back up a second. Negative time. Is that even that sounds like something straight out of a sci-fi movie.
It does, doesn't it? But to really wrap our heads around how huge this is, we've got to understand something called group delay. So picture this. A pulse of light cruising through space. Now, when it hits something, anything really, like a cloud of atoms, it usually slows down, right? Because it's interacting with all those atoms. Think of it like, how light bends when it goes through water. So this group delay, it's basically a measure of how much longer it takes for that light pulse to get through that stuff compared to if it had just, zoomed through empty space.
Okay, I'm with you so far. Makes sense. But how could there be a negative delay? Wouldn't that mean the light arrived before it even left?
Now you're asking the right questions. And the answer lies in the wacky world of quantum mechanics. See, normally we think of delays as, delays things taking longer. But in some pretty wild situations, like when light interacts with atoms under certain super specific conditions, this group delay, it can actually go negative. It's like the light got this sudden burst of energy from those atoms, even though it interacted with them.
Right, now my head's starting to spin a little. So how did the scientists even go about measuring this negative time? How do you even start to measure that?
Well, they came up with this ingenious experiment using supercooled rubidium atoms, and not one, but two lasers. Imagine the first laser is like a sprinter firing off pulses of light. Let's call it the signal, aimed straight at this cloud of rubidium atoms. Now, this signal, it's tuned to resonate with rubidium atoms. Think of it like hitting that perfect note to make a tuning fork sing.
Okay, I'm trying to picture this. Laser pulses, supercooled atoms. What about the second laser? What does that do?
Ah, that's the clever bit. The second laser, let's call it the probe boom. This one's continuous, and it shines right through that same cloud of atoms at the exact same time as those signal pulses. The really cool part, the probe, it can actually sense how much the signal has excited those rubidium atoms. It's like the probe can tell if the sprinter just energized the whole crowd, you know what I mean?
Okay, so let me get this straight. We've got these two lasers. They're both interacting with this atom cloud. And the probe laser, it's kind of indirectly measuring how long the signal pulse spends messing with those atoms, right? So what happened? What did they see?
And this is where it gets really mind-blowing. They found that, and this is the crazy part, for certain combinations of how long those pulses were and how dense that atom cloud was, the time they measured, the interaction time between the signal and the atoms, it was negative.
So are we saying they actually observed negative time? Did the light, travel back in time?
That's the million-dollar question, isn't it? It's not time travel like you see in the movies, but it definitely throws a wrench in our usual idea of time as this rigid one-way street.
Yeah.
It's more like it hints at a much deeper, weirder reality going on at the quantum level.
Okay, this is definitely blowing my mind. So if it's not time travel like we usually think of it, what are physicists saying about this whole negative time thing?
Well, to be honest, they're still trying to wrap their heads around it. I mean, it kind of goes against everything we experience about time in our everyday lives, but the math, the equations, and the experimental results, they seem to add up.
All right, well, consider me officially down the rabbit hole on this one. But before we get too far ahead of ourselves, let's pump the brakes for a second. I want to be sure we're crystal clear on how they actually took these measurements. They weren't like tracking individual photons, right?
You got it. They used something called a weak measurement. It's a way of looking at the overall effect of a bunch of photons on the system instead of trying to measure each individual interaction.
So instead of watching every single photon like it's a horse race, they're looking at the overall impact on the whole cloud of atoms, right?
Exactly. It's like instead of trying to figure out how each individual person feels after a concert, they're measuring the overall vibe of the crowd.
Gotcha. That makes a lot more sense. But even with this weak measurement thing, we're still left with this head-scratcher, negative time. What could it possibly mean?
Now, there's the question that has everyone stumped. And to really dig into that, we need to take a closer look at how this experiment actually worked because the details are key here.
Okay, so we're talking lasers, atoms, measurements so mind-bogglingly precise.
Yeah.
Break it down for me. How did they actually pull this off? What did the experiment look like in action?
Well, it wasn't just a matter of pointing lasers and hoping for the best. They had to get really, really precise, tweaking all these different parameters to see how it changed things. Like, for example, they messed around with how long those signal laser pulses were, from super short bursts to, slightly longer ones. They wanted to see how the length of time those atoms were bathed in light affected the outcome, you see.
So kind of like playing with a flash on a camera, trying different lengths?
Yeah, exactly. And they also tweaked something called the optical depth of the atom cloud, which basically means how dense it is. Think of it like adjusting the thickness of fog.
And all the while they were watching for changes in the probe beam as they were changing things up, right?
Right on. They zeroed in on something called the phase shift of that probe beam, basically, how much the timing of its waves got messed up after it went through that atom cloud, right after it interacted with the signal pulse. And we're talking teeny tiny shifts here. It took some seriously precise measurements to even pick them up. Like, imagine trying to spot a single grain of sand on a beach from space.
Okay, incredibly precise measurements, tweaking all these different factors.
Yeah.
And it's all to chase this idea of negative time. But how do they know these measurements weren't just, errors? How can they be sure they're really seeing negative time and not just some glitch in the data?
That's a great question. And believe me, these researchers, they were way ahead of you on that one. They bent over backwards to rule out any possible errors, anything that could mess with the results, any false signals, you name it. For example, they made absolutely sure that the probe beam's frequency, it was just slightly off from what the rubidium atoms would naturally absorb. That way, they knew it wouldn't get accidentally triggered, you see.
So kind of like making sure your car alarm won't go off if a truck drives by, right?
You got it. That's a great way to put it. They ran a whole bunch of checks. Like, they even ran the experiment with no atoms at all, and then they made the signal beam completely bypass the atoms and even tried blocking the signal beam entirely while they were still watching the probe.
Okay, so they had their control group, just like any good scientist would. What did those checks show? Any red flags popping up?
The amazing thing is, those checks, they came back squeaky clean. No signs of any errors that could explain away those negative time results. Sure, there were some tiny discrepancies, but nothing even close to being big enough to account for those negative interaction times they observed.
So we're back to square one with this mind-blowing negative time. It's like the universe threw us a curveball, and we're still trying to figure out if we should even be swinging.
It's a good thing we like a good challenge. And you know what makes it even more intriguing? These experimental results, they actually line up with some pretty wild theoretical predictions. There's this thing in quantum mechanics called the weak value of an observable, and in this case, the observable is what they call the excitation time, or how long the atom is buzzing from that photon.
Okay, you said it with a but, so I know there's a but coming.
And here it is. Unlike those everyday values we're used to, the ones that have to fall within a certain range, these weak values, they can be negative. They can even be complex numbers. It's like stepping through the looking glass into this whole other world where the rules of physics get, well, a little more flexible, shall we say.
This is definitely where I wish I had paid more attention in physics class. So we have these weak values, and they could maybe possibly explain how we can even get negative time. But what does it actually mean? Like, in the real world, what does it change?
No, that's the million-dollar question, isn't it? But we have to remember, this is just one experiment.
Yeah.
As exciting as these findings are, we've still got a long way to go before we really understand time, especially how it works down at the quantum level.
Right, it's not like we'll be building time machines anytime soon. Or will we?
Let's not get ahead of ourselves with the whole time travel thing. This experiment, it's more about pushing the limits of what we know about how the universe ticks. It's like finding a secret passageway in a house you thought you knew like the back of your hand. It tells us there's something much bigger, something much more intricate going on than we ever imagined.
Yeah, okay, I can get on board with that. But before we get too lost in all the possibilities, let's bring you back down to earth for our listeners for a second. What are they supposed to take away from all this? So we've gone deep down the rabbit hole with this mind-blowing experiment. We've grappled with negative time, and we've even dipped our toes into the wild world of weak values. But what's the takeaway for those of us who don't spend our days dissecting the quantum world? What does it all mean for the average listener tuning in?
Well, that's the amazing thing about this kind of fundamental research, you know. It's not always about finding a practical use for something right away. It's about expanding the boundaries of what we know, challenging the assumptions we have about how the universe actually works.
It's like that saying, the more you learn, the more you realize you don't know, right? This
Mhm.
experiment really seems to highlight just how much is still out there to discover about the universe and how it all ticks.
Exactly. And maybe the biggest takeaway is that even those things we think are set in stone, like time, might be a lot more complicated than they appear. Think about it. This experiment, with all its precise measurements and scientific rigor, it suggests that maybe, just maybe, our everyday experience of time as this straight line, this one-way street, it might just be a simplified version of a much stranger, more nuanced reality.
Okay, that's kind of humbling when you put it that way. To think something as fundamental as time could have these hidden depths that we're just starting to get a glimpse of. It makes you wonder what other mysteries are still out there waiting to be uncovered.
Absolutely. And while this particular experiment focuses on photons and those super-cooled atoms, it opens up a whole universe of questions. Could this negative time thing, could it show up in other ways on different scales? What other weird, mind-blowing phenomena are hidden just beneath the surface of reality?
I know what some of our listeners might be thinking. Okay, this is all fascinating and whatnot, but I got to get back to my daily grind where time seems to move at a snail's pace, especially on Mondays.
And hey, that's totally fair. But maybe, just maybe, this experiment can give us a new perspective, even in our everyday lives. So next time you're facing something that seems impossible, a challenge you just can't seem to wrap your head around, remember this experiment. Remember that our understanding of the universe is always changing, and what seems impossible today might just be tomorrow's groundbreaking discovery.
I love that. It's like the universe is saying, hey, don't be so quick to dismiss the impossible. Maybe the limits we see are really just thresholds waiting for us to cross.
Couldn't have said it better myself. Who knows what wonders are waiting for us on the other side?
On that note, we'll leave our listeners with a sense of wonder and a thirst for more. This has been an incredible journey into the mind-bending world of quantum physics. Keep those questions coming, because who knows what incredible discoveries await. Until next time.